Starting with a review slide. So this came from our spring break lecture on all of our mechanistic steps. I'm not going to go through with those. We've got our intermediates, and if we form an intermediate, we need to evaluate something about its stability. So in the case of the one-type mechanisms, both E1 and SN1, we get these carbocations. And remember, all the way back, we talked about stability of our carbocations, where the tertiary is more stable than the secondary, is more stable than the primary, which is more stable than the zeroary. So if we're looking at a reaction, is it likely to go through and form the primary or zeroary? And the answer is really no. So when we're thinking about carbocations, we should only be looking at carbocations in the secondary or tertiary kind of characteristics. Okay? So then the question becomes is, well, what happens if we have a secondary carbocation that is near a tertiary? Okay, so if we look at a potential example, what we end up seeing is a rearrangement. Because what can happen is that we can take our shiftable, if we want to call it that, species, and we can shift it with the electrons across to where the secondary carbocation is. The hope is that when we look at our new resulting structure, is that that new carbocation is at a more stable position. So in this case, we're making the assumption that atoms 1 and 2 are carbons, and that shifting atom was a hydrogen. So we went from a secondary carbocation to a tertiary. And because that is more favorable, it will happen every single time. So if you see this, or see a secondary carbocation near tertiary, you need to do the rearrangement. Okay? Don't worry about propagating out the rest of the mechanism until you've done this rearrangement, because we're always striving for more stable structures. But what if, when we look at our structure, let's say number 2 was a carbon, number 1 was a hydrogen, and let's say the shifting atom was also a hydrogen. Okay? What happens if we now do the shift? Okay? Well, if we shift that across, the result, if we quickly clean this up, is that we would then have a hydrogen here, or a new hydrogen. We'd still have a carbon, and we still have a hydrogen here. If we go through to define, in our starting structure, we had a secondary carbocation, and in the product, we have a secondary carbocation. Here, there was no difference in stability. If there's no difference in stability, that rearrangement does not happen. Don't do it. Okay? So we'll not string together a whole bunch of rearrangements, because eventually it becomes more stable. No. It has to be stable on that very first step. Okay? If it isn't more stable, then it doesn't happen. Okay? Or at least it doesn't happen with enough frequency to make it worthwhile. So when we tie this back to what we've been looking at with our, say, SN1 reactions. Okay? In our SN1, we break the bond with our leaving group first. So the result would end up being a secondary carbocation. Okay? And in some cases we'd say, okay, well, or in our generic case, we'd say, well, water is our nucleophile. It can share electrons. And we might predict, let's see which way I want to go. Let's go down, actually. We might predict this product forming, eventually at least. And the issue is that when we run this reaction, we end up not forming this product. We end up getting something different. We go, okay, well, what happened? Well, it might be helpful if we looked at what formed. What we actually end up seeing happen is we see this product, okay, where the oxygen attacked the other position. So what the heck? Why is that happening? Okay, well, that's happening all because of that intermediate. Okay, that intermediate is a secondary carbocation, because there's our positive charge, and that carbon that has the positive charge is connected out to 2 carbons. Okay, so we now have a secondary carbocation. Well, the issue with secondary carbocations that we must address is it possible to do a rearrangement? So we go back and we might look at this and say, okay, well, if I take the methyl group and I shift it over, what do I end up getting? I would get a secondary carbocation. Well, at best, it's a new secondary carbocation. Okay? At worst, it's the exact same structure. So that step doesn't make any sense to go through and do. So we say, okay, well, Mike, it shouldn't rearrange. Okay? one of the things you have to watch out for, I'll draw that nice and thick and heavy there, we have an implied hydrogen. What will end up happening is a hydride shift. The resulting structure will then be the carbocation there. If we go through and evaluate where the carbon that has the carbocation is connected to 1, 2, 3 carbons, and we have a tertiary carbocation versus secondary. That's more stable, which means my preferred mechanistic step is going to be to go through to do the rearrangement and not do the nucleophilic substitution, at least immediately. Now that I've formed my more stable carbocation, I need to permanently stabilize it, and this is where water can come in as our nucleophile. Sorry, I drew that way too big. Water can come in as our nucleophile, share its pair of electrons with our carbocation. The resulting structure, which I hopefully don't or have enough space for, okay, would be here with our positive charge on the oxygen. Oxygen does not want to be positively charged, so it can take electrons from one of the hydrogens to take us to our final product, our final rearranged structure. Okay. Just because it's here, we'll address it. You'll notice that in this case the textbook, because this came from the textbook, is being kind of nice, and they are specifying that we have 2 waters. Okay. So they're kind of being nice, because if we go back and look at this last step, say, well, that's not in our substitution mechanism, that's an acid-base step. Okay, what's going on there? Okay, well, again, if you think back to all the slides that we've gone through and talked about, when we talked about the general SN1, I said there might be an optional SN1 step, this or acid-base step. This is it. Okay. What they're trying to hint at is that to pick up that hydrogen, we need something else to pick it up, theoretically. Okay. And they're saying we have a second water molecule, now shown in 3D, to react with that hydrogen to get us to our final neutral state. I'm not one to particularly care about that. Sometimes textbooks get into it, sometimes other instructors will. So be aware of that. If you're losing hydrogens, it may be necessary to go through and specify. As one added wrinkle, just to kind of watch out for this, these are all equilibrium steps. They're all at least partially reversible. Okay. You should theoretically be able to realize that the secondary tertiary rearrangement is not very reversible. Okay. Because we're going to a much more stable tertiary carbocation. And then you should also realize that that acid-base step is also not very reversible as well. Okay. Yeah, so that's our carbocations. So we'll go ahead and stop that video and pick up again in another one.